Hello. I think we'll get started. My name is Iein Valdez. I'm in developer relations for Google Cloud and App Engine. And I'm here to talk about building reliable, redundant applications on App Engine using the High Replication Datastore. So I'm excited to be here. The talk is about the data store as it's become the new high replication version that we've released. We're not going to talk about the first iteration of the data store, which was master-slave. That was sort of the older version. We have our high replication, which came out earlier this year in January 2011. It's synchronously replicated. We'll talk about that, and it's much better. So this is the preferred persistence mechanism. So what we're going to talk about, for those of you that aren't that familiar with the data store and how it works, a little bit of history and background into why we created it, how we store data, what are the units that we use, which are entities and entity groups. Talk a little bit about its schema-less and why that is important. Talk about how we do transactions and how we do concurrency to give you some grounding in how the data store works. Then we're going to spend a little time and talk about eventual consistency and data freshness. And this has always been the challenge with these types of data stores. How do you create consistency with your data? And we have some tips and best practices to show you how to do that. And then I have some extra tips with some comic relief, with some good comics, talking about hot tablets, batching, parallel RPCs, and some really good things you can do with the data store. So that's the goal. We don't have much time, so I'm going to give it a go. But let me ask people in the audience, who here has used non-relational databases? So, yeah, OK. And then how many people use relational databases every day? OK. And how many people have used App Engine database, the data store? OK, that's good. So we have some good developers in the room. So awesome. That's great. So let's start into it. I'm going to summarize some of the core features, because App Engine is very big. We started in 2008. We have lots and lots of features. The platform has grown. So in one of my earlier talks, I talked about some of the compute services you have available. So we have front ends for request handling, 60 seconds or less processing. We have back ends, which gives you the ability to indefinitely process requests and live a very long time. Task queues to queue up work for processing now or later, either inside of App Engine or outside of App Engine, and then cron for scheduling work at a periodic time. So those are the compute services to run your code. And then we have the data store, storage. And we have lots of different ways to store data in App Engine. So we have our data store, which we started out with. We also have Memcache, which is a high-performance key value store. We have namespaces, so you can scope all of these things. Blob store to store blob data. Cloud SQL now if you want a relational database. And of course, we also allow you the ability to store static files and content and serve those up through App Engine. And an example of that is Google Doodles. A lot of that was static content. We also have network services, so being able to fetch out to other, make HTTP requests out, XMPP channel API, as well as mail API. So we live in a connected world, and you can use App Engine to talk to other systems. And then we have all of our services, and we've talked about services before. So we have, in one of the earlier introduction talks, we have Images API. We have something called App Identity, which allows your application to assert its identity to other applications within Google, as well as applications outside of Google. Users API, MapReduce API, Pipeline API, Perspective Search. So there's a broad, lots and lots of features, too many to talk in even one day if we talked about them all. But I just wanted to talk about all of it, paint you a picture of how big the platform is. But today we're going to focus on the data store. We're just going to talk about the data store, this one little piece. And even in that one little piece, we're not going to go too deep, but that's where we're going to spend our time. So why did we create the data store? Why does the world need another persistence mechanism? And the simple answer is we wanted to simplify storage. So one of the nice things about App Engine is you can write your code, deploy it, and it just runs. It's pretty simple. There are some constraints, but it runs. We wanted to do the same thing with data. I don't want to have to manage a database. I don't want to have to manage the schemas. How can I do that very simply from the developer's perspective? And so this is, we focus on the development, making it easy for developers, they write their app, to also persist their data. We also wanted to simplify the management of the data. So if you have a database somewhere, you have to back it up. You have to make sure you have copies of it running. You have to upgrade it. We wanted to simplify the management of your data store once you have it running. So that was another design goal. And then you have to simplify the scale, which means that you may have 10 people hitting your application, and that works great. But then all of a sudden you have 1,000 people, and then you're really popular, and you have 2,000 people and 10,000 people and possibly hundreds of thousands or millions of people. How do you do that without having to spend a lot of work on infrastructure? And so we wanted to make it easy to handle a variable request volume. And we also wanted to make it simple to handle different data sizes. So you may have a little application with 100,000 rows or 1,000 rows, or you may have billions and billions of rows. And how do you query fastly? How do you make that work? So we wanted to make it easy so you don't have to worry about scaling your data. And at the end, we built on top of all of the other services that Google has to offer. So we're lucky that we can build on top of the different levels of services that are already provided to us and other properties within Google, like Google Apps, and all those other things. We're able to use that same infrastructure that's in place to provide a high-quality service for your data. So on the right-hand side, you see some of the layers of what the data store is. And again, I talked about services. We have different layers. At the bottom, we have GFS v2, which is our next generation GFS. On top of that, we have something called Bigtable. And on top of that, we have something Megastore. And then finally, we have the data store on top of that level. So we build things in layers, but we don't have to worry about things at the bottom. As they improve, we benefit from those improvements, as do you. So the data store is schema-less, which means there's no enforced schema. There's not a notion of tables and columns. We'll talk more about this later. But you can use something called a soft schema, which is you can enforce a schema in your code. It's an object data store fundamentally. We have entities and entity groups, and I'll talk about that in detail. It also has a very powerful query engine for standard as well as custom indexes. So you can search, get your data out of the system and query for it quickly. And we also support transactions. If you have a database, you want to be able to transact sometimes. And so we support transactions. And of course, as I've said earlier, it's very distributed and very scalable. So if you have a lot of data or lots of query volume, you can handle that. So I just wanted to spend a second to talk about what is the high replication and the high replication data store. What does that mean, high replication? So what it means is that when your data is committed, when you write a piece of data, it is synchronously replicated across multiple data centers, across multiple geographies. So your data is simultaneously written everywhere. Or not everywhere, but to wherever the data is stored. So that means that essentially you have high availability and reliability because you're no longer having to worry about maybe a master-slave relationship where there's only a master and a slave and you have to take one off. We actually push it to multiple copies, and that allows you to have consistent performance because if we have one of those data centers that is acting erratic or slow, we can take that out and we can still serve traffic for you. And you don't have data loss or downtime because again, we have lots of copies running in lots of different places. So the high replication data store is very powerful. The magic we use to make it all work is an algorithm called Paxos. You can type in Google and you can get some information about how Paxos works, but that's one of the technologies that's allowed us to do high replication data store. So let's talk a little bit about how we store data in the data store. And the fundamental unit of storage is something called an entity. And an entity has a kind, which you can think of like a table in the SQL world. So the kind might be an automobile. It has a primary key or an ID, so you can fetch the entity or uniquely reference it. You can put it within what's called an entity group, so you can partition your data, or you can create this hierarchy so you can create data locality, and this is part of how we do transactions and consistency, and I'll talk in detail about that later. And then one of the really good things about an entity, and this is what makes it dynamic, is that you can have an arbitrary number of typed properties. The properties can be variable by entity, and they can be multi-value. And that's really important. So you may have very sparse data, which means you have certain entities with a few columns and certain other entities with lots of different columns. The fact that you have this variable properties allows you to store lots of data within a certain kind and in a very efficient fashion. And this is part of the big table and some of the other technologies that we have. But this is how we store data. We think of an entity. It's an object. So let's walk through a sample of what an entity. Oh, you can't see my slides up here. Okay. Well, let's walk through an example of how we would write an entity in Java. Let's see. I'm going to try to zoom in here so we can actually see some of this. The first thing we do is we import our data store service and factory, an entity. And we then instantiate the data store service right here, which is what allows us to store the data. And then we create an entity, and we call it employee. And we say we want a kind of employee. So this is the kind right here. And then once we have it instantiated, we take that instance and we can add properties to it. So first I'm adding a property called first name, and I put my name here, last name here. So this is of a string I'm writing. Then you can add other kinds within Java. So here I have a date, and I'm going to store a property called hire date. And the other thing is you can also have properties that are indexed and properties that are unindexed. So maybe I don't want to search on t-shirt size. It's not important to me. So I can set it as an unindexed property. And you can, of course, change this later. And then I set a Boolean value, and then I just write put. So I create the entity, and then I put it, and it just works. So it's pretty simple. There's not any complicated stuff going on here. Let's see here. I don't know why it's not showing you the top, but maybe I'm going to do it right here. OK. So let's look at an example here of how to query entities. So I can write an entity, but how do I get it back? So we get the data store service. Oops. Sorry. Skip through here. OK. So we get the data store service. And then we create a query, and we say, what am I looking for? I'm looking for the kind of employee. So you specify the kind in the query. Maybe it's better if I zoom in. And then we add a filter to the query. And so this is, in a SQL world, this is sort of like adding a where clause. The filter is, I'm looking for last name where it equals Valdez. So I'm going to get all of the kinds employee where the name equals Valdez. And then I put it into a prepared query, and then I can iterate over and print it out. So it's a pretty simple process to query entities. So that hopefully gives you an idea there. Next, let's talk about Schema-Less. So why is Schema-Less a good thing? There's arguments that go both ways. I'll make the argument for why Schema-Less is a good thing. If you're a developer building an application and you have data that changes a lot, you're not exactly sure, your data model isn't set in stone, maybe you're a startup, you're adding things all the time, changing things all the time, rapidly evolving data is a really good candidate for these types of databases, data stores. Development speed is really important. So I don't know how many of you have, you've been writing a local application in a SQL database, and you say, I got to change, I got to widen the column because I really meant to go from a char to a varchar 64. So then you have to alter the table, and then you build your application, and you say, I have this other required property I want to add into my database, and you do that, and then you want to deploy it to your production server, and you forgot to migrate or alter your schema in production. That's a very slow process. That makes it really hard. In a schema-less data store, you don't have to worry about migrating your data. You can just change values and properties on the fly, and it works. You can also have heterogeneous data types, which means that, let's say I have a car with a model property. The model property could be a string, or the model property could be an integer in two different entities. So you can mix and match these things, and it still works. And then I had mentioned earlier sparse properties, where you have a car with 100 properties over here, and you have 1,000,000 cars over here with 1,000 properties. It's allowing you to have variable number of properties per kind. It allows you to store sparse data very efficiently. And again, what do you avoid by using a schema-less? You don't have to worry about schema management, no more ERDs, no more alter tables, migration, DDL. That stuff is hard work. And then you don't have the schema sync problems I mentioned. When you're doing local development, and then maybe your colleague is also doing development, and you're deploying somewhere else, you don't have to synchronize all of your schemas and migrate your data. It gives you flexibility to build. And again, these are a couple of different scenarios where this is painful, where you're adding a new required column or you're changing the size of a column. So let's just walk through some code here. And the title here is "It's easy to add properties without schema management." So the employee entity I wrote later, let's say I pull 2 instances of that, and I want to add a new property called mail slot. So I have two instances here, employee 1, employee 2. So I can set a property here, and then I can write it back out to the data store. But then let's say, employee 1 doesn't have that property anymore. So I can actually just remove it by, I already have it instantiated. I can just remove the property, and then I can put it back out. So it's really easy to change it. It makes your data very dynamic. And then the good thing is you can have a situation where you don't know what properties are where. You can actually take the entity and you can query it and say, tell me what you have. What are the properties that you have? And then you can get those properties back and then do something with it. So it's pretty flexible. So, okay, so we know what entities are. We can store objects. What is an entity group? Why do we have entity groups? Entity groups is what allows us to do transactions and make sure your data it gives you an ability to make sure your data is either strongly consistent or not within queries. So, and we'll talk about this in a minute, but it's essentially a logical grouping of entities, and it creates a parent-child relationship. So if you have an entity with no parent, it's what's called a root entity, and it's standalone. If you have an entity with a parent, then it is in the entity group, and the parent is at the top of the root of the entity group, and you can have parents with parents with parents. It always goes up to the highest parent within the entity group, and that is the locking mechanism going down. So we'll see some examples of this in a second. So here is an example of entity groups. We have comments. You can imagine this is a blog. So we have a user, we have a blog, another blog, posts, and these are all different entities. But what we have here is a relationship. This red line shows the parent and the parent. And so the root entity of all of these entities here is user. That is what controls it all. And so transactions will lock at that level. So if any of the children are in a transaction and try to change data, it binds all of the children of its root. And this is what creates transactionality for us. And we'll go through some examples of that. How do you create? Let's just walk through a little bit of code that shows how you can create an entity group. First, we create a root called root. It could be called anything, could be called parent. And we write it out. And we also save its key. And then the next thing we do, and so this is the picture of what we did. We just wrote an entity out. It's just an entity on its own. So next we say, well, let's add some children to that. How do you add a child when you write the entity, or how do you add a parent when you write it out? So we create a new entity called child, and we say it's of type item, and you specify here the parent. Who is the parent of this entity? And then you can set the properties, and then you can write it out. And what we did is basically, I'll play this. So what we did is we had the root, which is when we created the item, we set the root as the parent, and that created a relationship. And all transactions then lock all the way up based on the root. And so, I just went through this. The thing about transactions, they only apply to a single entity group. And we actually have a new feature I'm going to talk about later. Before, if you had one bank account that was in an entity group and another bank account, you actually had no ability to do transactions across those entity groups. There was no way to do it. You had to do some work on your own. We have something called cross-group transactions, which solves that problem, and I have some slides to show it. The other thing is you can perform a query during a transaction, but only if it includes an ancestor, meaning you're looking for the parent. If you don't do that, the query will still work, but you can get stale data, and this is where you get, this is eventual consistency. So what is eventual consistency? I don't know if you have these things out here. We have checks, which are promises to pay. They come from our bank account, and you write a check, and you give it to somebody, and you hopefully will eventually get the money into your bank account, but you're not really sure. Maybe they have enough money, maybe they don't have enough money, you're not sure, but this is an example of eventually consistent. So in the data store, if you're running an eventually consistent query and someone writes data, you may get an old version of the data. You're not necessarily going to get a new version of the data. And I wish this was working. Okay. And this is an example of an eventually consistent query here. So we have an entity, but you'll notice we construct a query, but there's no ancestor. So we're just saying, give me all of the items. And so this example, you can get not very, but you can get outdated data. 3 people may have just written new items a second ago, but you may not see those. And so this is eventually consistent. Now, in some cases, that's okay. In other cases, if this was a banking system, you want to know if other people are doing transactions. You want to always read the latest data that was committed. And that's strong consistency. So this is basically an example of strong consistency. So cash. You give someone cash, they have it in their hand. It's instant. Versus the checkbook, which you don't know if you're ever going to get the cash. So strong consistency means when you do a write, the next read will immediately return that write. So you always get the latest view of the data. Always get the latest view of the data. And this is tricky with these distributed databases, and this is why we have entity groups, which allows you with an ancestor to create a query that is strongly consistent, which means you always get the right data. So let's look at a strongly consistent query, a query that will always give you the right data. So in the previous example, we created a query, just like this one. However, in this example, I set the ancestor here. And so this is saying, give me a query, but I want you to look within this entity group always. And that is what will then cause our query engine to return the right results to you. I'm going to add a filter, and then, of course, I'm just going to run my query, but I will always get the real data, accurate, up-to-date data using this query. Here's another example of a strongly consistent query. If you know the key of an entity, or the ID, and you fetch it, you will always get the latest version of the entity. So let's say 10 people have the same entity and someone changes it. The next one that queries it, even though if they're using the key, they will always get the latest version of the entity. So this is another good way to specifically fetch and get strongly consistent data. So the question is next, you can't always have strong consistency. So how do we deal with the cases where we have eventual consistency in an application? And there's 4 common patterns we have here, which is you do a code audit to find global queries, and I'll show you an example of that. You can accept it and say, it's okay for me to have data that's out of date a little bit. I don't really care about it too much. It'll catch up. You can avoid it, or you can work around it. And I have some really good examples of this. So let's look at some of these examples here. So what we have up here is the first case, which is you want to find all of the global queries. And what is a global query? A global query is a query that has no parent in it. So you see this example here. Let me move down. We're doing, this is pseudocode. You see a select here. We're saying select star from comments where blog ID is such and such, order by this. And you see we have 2 different entity groups over here. One user on this side, one user on this side. So if the user on the left-hand side creates a new comment and you use this query, you may not see it. There's no guarantee you're going to see it right away. So this is what we call a global query. So how do we solve this problem? Well, again, one way is you just accept it because you have a lot of queries that you don't actually require strong consistency. So an example of this is, let's say you have a homepage and you have new news headlines that kind of post to your homepage. You might not really care if there's a new article posted 35 milliseconds ago. You might not really care about that. You might say it's okay if that article shows up in my feed a second from now or 2 seconds from now. So in some cases, it's okay to say, you know what, I don't need I don't need strong consistency in this case. So you can just accept it. Another thing you can do is you can avoid it. And so let me just play this slide so you can see the animation properly. If it comes, maybe. This is not, okay, well, we won't. So on the left-hand side, you see we have a bunch of entities. We have 8. And one way you can avoid it is you can group them. You can create the hierarchy, create parents, create parents, create parents. And on the left-hand side, we had 8 root entities that were standalone with no parents. And we changed the data on the right-hand side to say, yeah, there's 2 users and everything falls underneath that user. One user has a blog, one user has a post, one user a comment. So we created 2 different entity groups. And now we have an easier way of organizing the data. So this is create larger entity groups is another way to deal with this. And then the third way, which I think is very, very clever, is to mix in, to do a hybrid approach, which is to take a strongly consistent query with an eventually consistent query, and you mix the results in. So in this example, there's all of these different visitors. And all these different visitors have different comments. And you do a global query, and you say, give me all the comments that are out there. But the visitor goes to the website, and he puts a comment, and he wants to see his own comment right away. How do you do that? So you do the global query, and then you do a ancestor query on the visitor's own entity group, so you can get always the latest comments that this guy is doing and mix them in with everyone else's comments, so you actually get a pretty good, you get an accurate view of the data. So this is another good strategy. There are some limitations to entity groups. You want to try to limit writes to 1 per second. This is a little confusing because when you say a write, it's not writing one entity. You can write millions of entities at once, but within the entity group, when you do a write, just don't write more than 1 per second. Don't commit more than 1 per second. And in practice, you get 5 to 10, but the rule of thumb is try to limit it to 1 per second. So if you think about it, if I have my own entity group, it's unlikely that I'm going to be changing data more than once per second myself. And again, you can have arbitrary sizes per write. So let's look at the contradictory advice with entity groups is that you want to make them as big as possible to put as much data as you can underneath them, but you want to make them small enough that the write rate stays within the 1 write per second. These are sort of best practices. So I mentioned something called, let's say we're in a banking system and we want to be able to transact across entity groups. How do you do that? Well, before we didn't have a mechanism. We just released in 1.5.5 something called XG transactions, which are cross-group transactions. It allows you to access between 1 to 5 entity groups and read and write from them, and as well as transact across up to 5 entity groups. So this is actually a really nice feature. We've had lots of developers asking for this, and it really helps a lot. Now, some things to note is on your first access, you could actually get an exception, but you can catch that and handle it. This is only available in High Replication Datastore applications, which is another reason to use the High Replication Datastore. And if you have non-ancestor queries, you can also view partially committed data. So it's just something you need to be aware of as you're using it. To give you an example, let's take a look at what a cross-group transaction looks like in Python for the Python developers out there. Here we import our DB module, and what we're trying to do here is basically we have 2 entity groups, 2 different bank accounts in 2 different entity groups, and we want to move money from A to B in a transaction. Before it was really hard, now it's really easy. So we have a Python decorator at DB transactional XG equal true on top of this function called transfer funds. And once you put that decorator on and you commit the data here at the bottom, that handles all of the work to commit the transaction across entity groups. So it's super easy to use. We have another example in Java for the Java developers out there. It's more complex, yes. I hear some chuckles, that's good. But basically, in Java, when you write a transaction, you instantiate a transaction and you pass transaction options. You set a function called with_xg true, and then you commit the data normally, and of course, the cross-entity group transaction will be handled for you. So it's a few lines of code, but you're able to do that. So let's talk about some tips now, some tricks that people that use the data store may or may not know. So one of the biggest tips is to use batching. And what batching means is that let's say you want to pull 100 items out of the data store. Some people just iterate in a loop. Give me this one, give me that one, give me this one, give me that one, give me this one, give me that one. And it's just a lot of different round trips. So when you batch, you can say, give me all of the give me all of the entities in this range, and you can get 100 things back. And so instead of having 100 little round trips, you can actually get one round trip. And if you look at this graph, this is using AppStats. You can see that there were lots of little requests done. And when you did batching, you actually reduced the total time. So you went from almost 400 milliseconds down to 200 just by using batching. So use batching. When you call it, you can do db.get and pass in a list of keys, or you can write a bunch of entities at once. So instead of writing one by one, you can write hundreds. And also you can do the same pattern with memcache. So batch. Use batching. That will save you time. The second thing you can do is use Parallel Rpc Requests. So there's actually an asynchronous version of the data store service that you can get in Java and in Python. And in this example, we do a db.get async call, another db put.async, and these things go run asynchronously. They don't block. And so you can do lots of these asynchronous calls. And if you look here in this graph, you can see the effect of doing things asynchronously versus serializing your gets and writes. So it saves you a lot of time again. So another best practice is to use asynchronous. Okay, so now we're going to get to the fun part in a second and the comics. Another big tip that developers run into with these types of data stores is we like to call it hot tablets, which is that if you're creating a lot of objects and the keys, the unique identifiers, are serial, it actually starts sending a lot of traffic to a specific tablet server. And the tablet server starts getting really busy. And then we have lots and lots of different tablet servers, but if the keys are just slowly incrementing, it puts a lot of pressure on this one, and it will actually split. But then when it splits, it still has the same problem. So the data actually just runs because of the way you generate keys. That actually can put pressure on a tablet server. So we have some tips, and I think the best way to see this is to let's look at a graphic here. Oh, this isn't working. Okay, so we'll just play it like this. So Iein is also works in developer relations, and he's a very passionate software developer, but he's also a cartoonist, and he has talent, and he can draw cartoons. I unfortunately have no talent. I can code just barely, but Iein has some good talent. He can code and draw cartoons. So he drew some cartoons to explain how hot tablets, what they mean and how they work. So what you see here is a picture of a tablet, and you see writes coming into the normal tablet. So he's very happy, right? Let's see. But then he starts seeing lots of writes coming and lots of writes requests, and these tablets start getting hot. It's like, too many writes, I must multiply, I'm too hot. And so what happens is, and this is again how our infrastructure works, there's a moment where we pause everything, and we create a new tablet. So we split them things out, and now there's another tablet server. And so we have two tablets that are very, very happy. And the guy on the left is, woo, I'm really happy, thanks for helping me out. And the guy on the right is, yeah, no problem. And so this is how we handle load. We split these things out. It works great. However, during the split, data store RPCs back up. And performance slows down while we're doing the split, but then it catches back up. So you don't want to do a lot of these splits because it slows your application down and can create a little bit of instability. The other thing about these is that the high write rate, you want to distribute writes as much as possible, so you have to be really smart about how you create your keys. And this was the original problem I'm talking about. So in this example, this is kind of a crazy picture. Let's see if I can get it here. Right, I need to zoom out just a little bit. Here is a picture on the left-hand side of a tablet, and he has writes coming in, and the names are keys. Dog, zebra, gopher, walrus, and he's starting to get hot, and he's like, I got to split. And so, Shazam, he splits up, and because the keys are, distributed, this tablet can take some, and this other tablet can take some. So the load is distributed evenly. However, we'll go to the next one. If you don't have keys that are distributed well, and in this example, you have monotonically increasing keys, so you're going 1, 2, 3, 4, 5, 6. Writes come in, the tablet gets, hot. And he says, I got to split. He splits, but the keys still go to one tablet. And so you have one guy on the bottom here who doesn't get any new writes, and the guy on the top still has more and more and more writes, and he splits again, but he still gets more and more writes. So you don't want to use monotonically increasing keys if you have a high write rate. And so we have the tip here is basically right up here. What do? You want to, if you use your own key names, you want to try to randomize the keys. Use just different names. Don't use a function that monotonically increases. Prepend a hash or MD5 or some some other data that can actually help distribute the keys out. So that is another example of a best practice. So you want to use asynchronous when you can, and try to distribute your keys. So that basically was what I wanted to talk about, and I'm happy to take some questions. Thank you for your time, and I appreciate it. Yeah.
I have a question. You said that it's advisable to do around 1 write per second per entity group. Does that mean like 1 write per 1 object, or write means DB put and the list of entities, let's say 100 of entities in that entity group?
Yeah, you can have millions of entities in the group per write.
Call one write is defined as 1 DB put operation.
No.
It's one object or 100.
Yeah, it's within the entity group, yeah. So, yeah, I think...
1 write per the entity group.
Per the entity group, but the write you can put millions of objects within the entity group. Yeah. No, not just one. You can put millions within that one write. Yeah, so if you imagine everyone in this room is their own entity group, every person could write millions of objects each simultaneously per second. Yeah. Yeah, so it's not everyone, there's just one thing at a time. Yeah. Yeah, that would not be good. Yeah.
Is there any significant difference in performance between the eventually consistent and strong consistent?
Yeah, so the question was, is there a performance difference between eventually consistent and strongly consistent? The answer is I don't actually know. I haven't actually tried it out. They're both pretty fast. I would think you would get slightly less performance, but I don't know. I can look into it and get back to you. I don't have the answer. Conceptually, it would seem it would be a little bit slower. Yeah. Any other questions? Yeah.
Yeah. About the incremental key updates.
Yes.
If you just let F-engine assign the keys, you don't have the problem.
Correct. Yeah. It's only if you specify your own function that is creating this monotonically increasing function. Yeah, exactly.
Does it also apply to the data? For example, if you have a monotonically increasing timestamp on each entity you are cooking?
No, it's only with the keys. Okay. It's only with the keys because that's part of the key path when we write the object out. So yeah, you can have anything in any other part of the data. The key is really important. Yeah. Yeah.
About the key, so it means it's a really bad idea to have a prefix.
Yeah, a prefix that is distributed pretty well. Yeah, so that's right. Any other questions? If there are no other questions, you can just come talk to me. I'm happy to look at some code. We have a session right after this, which is a hands-on code lab. So you can also bring your questions there. I'll be there as well as Fred Sauer from the App Engine team. So thank you very much. I appreciate it.